Thanks, Pallavi, and thanks to the organizers for
can
putting
also
together
give,
this conference. Okay.
All
right. Okay. So I'll get to the cosmology part first and the experiment part next. But I always flash this slide at the start of any of my talks to just show, what the team is. But today, for the first time, I kind of paid attention, did some statistics, and we're 8 out of 19. We're not quite 50% in our lab, but we'll get there. Okay. So, right. So quickly, I'll just start with a very basic picture of standard cosmology. So the current standard cosmological model, we call the lambda CDM, or dark energy and cold dark matter. And in this, our clock starts ticking at some T0. Today, we won't ask what happens behind or before T0. We don't know. But that's the left part of this plot, okay? So popularly, this is called the Big Bang. So today, I'll continue to call it Big Bang, okay? We don't exactly know what happens in the Big Bang. We don't think something goes bang, but definitely it's a very energetic process. And within the very first few minutes after this Big Bang, the universe is filled with radiation or energy, as well as baryonic matter, which in astronomy and not physics also includes electrons, okay? So we have protons, electrons, some helium nuclei, and very little amounts of other trace elements, light nuclei. Gradually, the universe expands and cools down, and this allows electrons to combine with the protons and helium nuclei to form the very first atoms in the universe, first stable neutral atoms, okay? So this leaves us with energy and helium and hydrogen atoms. There's also dark matter and dark energy, but for the work I'm going to talk about today, that's not very important. So gradually, this hydrogen and helium form stars, and these stars explode, give you heavier elements, and we are here today. But the radiation that I talked about from the very early universe comes to us today, and we call this the cosmic microwave background radiation, or the CMB. So if you go and look up CMB on Google, you'll see various pictures. This is one such picture. This is from the Planck telescope. And this is from the 2018 data release. And the CMB is a very nice black body. So it has a black body spectral distribution. And this, what you're seeing here, is the fluctuation around the black body temperature. So the black body temperature is about 3 Kelvin. But in some places, it is little hotter than 3 Kelvin, and some places it is little cooler than 3 Kelvin. And that is what this picture is of, okay? So this is a nice thing to put things into perspective, because we can't really appreciate how far back in time we're looking when we're making images of the CMB, all right? So this is the cosmic calendar. It's please look it up and spend some time on it. So if I compress that entire image that we think of as the history of the universe, and the universe is about 13.8 billion years old today. So this is 13.8 billion years squeezed into a calendar year, okay? So the Big Bang is on the midnight of Jan 1st of that calendar year. And when I'm giving this talk is right now, which is December 31st, almost 11:59, okay? So humans came into this picture in this cosmic calendar on December 31st, say 11:50 p.m. I know where humans start is a different question, but around 11:50 in the night of this calendar year is when humans came into the picture, okay? For context, dinosaurs were December 29th. We are looking something like, I don't know, 5th of January in this calendar year. That is how far back we are routinely making images or studying the universe way back then, okay? So like I told you, the CMB has been measured to have a black body spectrum. This was also motivated theoretically. And this measurement has come to us from the experiment FIRAS on board a satellite called Kobe, which flew several years ago, okay? This is in the 60s, early 70s, okay? So it's been like 50 plus years. And you can see that if you plot intensity as a function of frequency, these are the points, and the points have been exaggerated and blown up so that you can actually see it on the curve. So this is the curve that fits to a black body, and these points have been exaggerated so you can see how good the fit is. Okay, this measurement is to 1 part per 100,000. Okay, that is how well COBE has measured the spectrum to be a black body. But there are two things. First is that if you extrapolate this plot down and you actually zoom in at the measurements that have been made in the few gigahertz or few hundreds of megahertz frequency range, the error bars are huge. Okay, and this could be partly because there are experimental challenges, but there's a lot of interesting astrophysics and cosmology that can lie in these error bars. Okay, and that is my interest. So there are various theoretical motivations that tell you that the CMB spectrum should not be an ideal black body. There should be deviations of the CMB spectrum from a black body by processes that either inject or remove energy from the CMB photon bath. One such process is the formation of the very first atoms. So when I told you that these electrons combine with protons and helium nuclei to form atoms, the process of formation of an atom, so you can think that there's an electron at some higher principal quantum shell number, and that gradually trickles down to the ground state. This gives us a stable atom. But every trickle down or every transition of this electron emits a photon, right? Those photons must be out there. And that is a theoretical prediction, that is an inevitable prediction of standard cosmology, that there must be these photons still present in the CMB photon bath. It just so happens we have not measured the CMB to that level. And the level we're talking about is about 1 part per billion. Okay, so the current best measurements in the spectrum are 1 part per 100,000. So we have to go at least 4 orders of magnitude better in our measurements, and we will see these spectral distortions in the cosmic microwave background that comes from the first atoms. If we don't see them, that's a big problem, because this is something that is at the bedrock of lambda CDM cosmology, right? So this blue line in spectral density units is the CMB spectrum. It turns over nicely at around 150 gigahertz or so. And down below here in orange is the spectral distortion, the additive photons that comes from the formation of the first atoms. And highlighted in green is the band that I'm building an experiment at RRI to try to detect these signals. We don't go to higher frequencies for 2 reasons. One is you start going to higher frequencies. For this level of accuracy, you have to start going to space, and it's complicated. The second reason is just from a signal to noise ratio point of view, and to be able to separate the signal you are seeing from this structure from everything else your antenna will see. This was chosen to be the ideal band for a ground-based telescope. Okay, so if I zoom in there, over about 1 to 7 gigahertz, this is the spectral distortion that comes to us from the first atoms. So each of this is actually an alpha transition of the hydrogen line. So those who are familiar, you have H2 regions in the galaxy, and you have radio recombination lines. These are cosmological radio recombination lines, okay, dominated by hydrogen, but you also see some signatures of hydrogen and helium feedback. So this also gives us an experimental way to measure pre-stellar helium abundance. Okay, now coming to quickly, you put together a telescope, you have a nice antenna, you have an analog digital receiver, you have some way to analyze the data. Okay, and what you measure is not those lines. Okay, you will measure something like this, which is mostly the CMB, about 3 Kelvin, as well as some contribution from your own galaxy, right? So this is what our galaxy looks like at 408 megahertz. It is very rich in structure. You have a galactic plane, you have loops and spurs, and all of this will show up in your data, okay? So what you need to do is to first be able to understand what is it you're looking through, then to be able to separate your local signal from your galaxy, and then extract the cosmological signal. If you have a poor understanding of what your galaxy can contribute in your spectrum, you will not be able to make a high confidence measurement of the signal you are looking for. Okay, so to remind you, signal is at the level of tens of nanokelvins. Your CMB plus your foregrounds could be few Kelvin. Add to that atmospheric contributions. Typically, you have about 10 Kelvin in total in your measurement. So you have to build an experiment that has a sensitivity or a dynamic range of 1 part per billion, right? So the first step you do is to see if theoretically, can you separate the two? Can you separate the cosmological signal from the galactic contributions in an ideal instrument? And for that, we've come up with some mathematical methods. And this is just to show you that if in my simulations, I don't have the signal, cosmological signal, I go to basically numerical noise levels. But if I do have my signal, I do have a technique using my mathematical algorithms to be able to recover the signal I put in. Okay, so now we have everything sorted out. You have a model of the galaxy that you understand to reasonable accuracy. You have a way to separate the signal from the foregrounds. Now you have to go ahead and build the telescope, and that's what we're doing. So this experiment is called Apsara. It's an upcoming S-band cosmology experiment. It stands for Array of Precision Spectrometers for the Epoch of Recombination. So clearly, as the name states, eventually when it is complete, it will be an array of mini radio telescopes. And right now, the focus of this talk is on the prototype element of this radio telescope. So in and of itself, the first element, we're trying to target a sensitivity of 1 part per 100,000. So basically get to the Kobe Firas level accuracy at the few gigahertz frequency range and reduce these error bars I showed you in the first slide. So this is the target of the prototype element. And while we are doing this, there is a mysterious signal people have been seeing at radio frequencies. And depending on who you talk to, they'll tell you whether they think it's real and exciting, or they tell you it's just nonsense because of poor data analysis methods. So people have been seeing what they call an excess radio background, which telescopes have picked up. And this telescope, Apsara, that we're building, the prototype element, should have the sensitivity to be able to say whether or not this excess radio background is real, okay? Eventually, we want to scale this one prototype element into about 100 such elements and then get to the sensitivity level of nanokelvin by observing the sky for at least one antenna a year. Okay, so the kinds of things, now I come to the experiment part. So I motivated the problem. So the kinds of things we have to do for this is we have to start making our own custom antennas. So standard antennas for radio telescopes may look like a dish, they may look like a dipole. But when you want to operate an experiment at this 1 part per 100,000 sensitivity over a wide frequency range, you will have challenges like your antenna beam, for example, may look slightly in different directions of the sky at different frequencies. This would end up leaking different parts of the galaxy into your spectrum at different frequencies, which means your foreground signal can start looking like the signal you're trying to detect. And your algorithms to separate the signal from the foreground start failing. So you have to custom design antennas that have a very stable beam to your measurement accuracy over the entire frequency range of operation. So for this, Kirtipriya has designed what we think over this frequency range is the most stable beam antenna over 2.5 to 4 gigahertz. We started at 2.4 gigahertz because of radio frequency interference related issues at our initial planned deployment site. So we focused on 2.5 to 4 gigahertz. So with this, she has been able to design an antenna that when we put it through our pipeline, we see the residuals or our sensitivity is at the level of 1 part per 10,000 to 1 part per 100,000. So it doesn't stop here. We actually make these antennas. We go and we test them in anechoic chambers as well as on the field. And this is a zoom-in image of one of the antennas we've come up with. So in addition to designing the antenna, she has also worked on coming up with very interesting mathematical algorithms to improve the frequency stability of these antennas. So you go away from a standard model and optimizing using parameters, but you study the surface currents on these antennas to make the antenna more stable. So we have come up with even methods for improving our antenna design. So next we start building the radio receiver. It looks quite complex, but finally at the end of the day, it's a high precision, self-calibratable radiometer. So you have the antenna here, and there is this entire structure in this black box sits in a cryo-cooled receiver. So it operates at 77 Kelvin. And with this, we have a noise source, a cold load, and a warm load at room temperature. So you have a way to calibrate your antenna measurement against some absolute temperature measurement. So we don't calibrate on the sky, we calibrate with our own sources of noise at different temperatures that we have some information and control over. And the rest of this is basically to reduce noise, amplify, and so on. So this is a picture of the setup in the lab right now. This is this cryocooler, which has all our electronics at 77 Kelvin. You have to operate it under vacuum, otherwise you'll have condensation, you can't maintain the temperature. So this is a vacuum pump that maintains ultra-high vacuum. And inside this, we routinely test our electronics and test our calibration. So next, you take this analog signal and you digitize it. This is a previous, like a legacy board, which had a 4-bit digitizer. And now we have moved to ZCU111, which is, I think, 12-bit. It's a 12-bit board. And again, this samples, direct samples, up to 4 gigahertz for us. Okay. And so this work has been led by Shrivani and Girish. So the other kinds of things that this work involves is you have to go out and find radio quiet locations because the signal you're looking for is extremely faint. So we have our base station for all our field operations is the Gauribidnu Radio Observatory, 80 kilometers from Bangalore. It is not the ideal site for this experiment because of radio frequency interference, but this is a good place to start deploying and get the hang of deploying a cryocooler on the field. So we up to 2.5 gigahertz, this site is unusable for this experiment. 2.5 to 5 gigahertz, it is still okay. We will continue to see satellite downlinks, but that is something we can take care of by flagging. We have gone to various locations in Ladakh. We've also had a team member go to Svalbard in the Arctic and conduct RFI measurements. For right now, the plan is to deploy in Gauribidnu shortly and then move it up to Ladakh. Ladakh also helps because you have low amounts of water vapor in the sky, which starts becoming a problem at these frequencies. So the higher in frequency you go, the atmosphere itself starts adding to your receiver noise. For example, and water vapor is a factor that will start adding to our final system noise temperature. We've done some simulations about where we think the site quality will be good in terms of low water vapor. And last summer, we went and we deployed a small setup that can measure this water vapor content at the Hanle Observatory. And the hope is that once we have this experience, we can also scale this up and take it to more remote locations to find the ideal site. Hanle will be the base for all of this work. So this is at the IAO Observatory in Hanle, and we thank IIA for all the support they gave us to get this done. So here are just some behind the scenes pictures of what every day can look like. So this is us when we just commissioned the cryocooler in the lab like about a year ago. RRI lawn, if you've ever visited RRI, is the place we go to for quick tests and just testing things out. So this is us making some measurements here. So what the work can look like is the experiment side of things looks like designing antennas, working with digital and analog receivers, co-designing it with a team because it always is a team effort in building these electronics. Finally, you get to go on field expeditions for observing, analyze data, build algorithms. Vishaka and Kirti here on a very, very hot day in Gauribidnu making some measurements. And at the end of the day, we're all doing this to get the science done. So I'll stop here and take any questions.
Thank you, Mayuri. Questions?
Sure, I can hear you.
That could work too, I think, yeah.
Yeah, thanks for the nice talk, Mayuri. I just wanted to ask about this radio excess. When you showed that plot, I couldn't really make out
Sure.
what is the excess.
That's not a great plot, I agree. Okay. So this is actually the plot of the excess. So if you see here, this dashed line, I think is the CMB, right? And this line is the synchrotron background that you expect. And here people have started seeing that when you make a measurement of the radio spectrum of the sky, let's say, you have some expectation of what you would see in that direction from our galaxy because of power law. And then you have some source counts from various galactic catalogs, extra galactic catalogs. You total up everything and you have a typical number of what you should measure. People have measured more than that. Okay, for example, at 3 gigahertz, 3.3 gigahertz, there's an experiment called Arcade 2. It was a balloon experiment. I think it saw an excess of about something like 33 millikelvin or something like that at 3.3 gigahertz. The contention is that they have done their galactic contribution modeling wrong. That their model of the way the model of your what you expect from the galaxy through that line of sight has been done wrong. That is one contention. But multiple experiments using different techniques continue to see this excess.
In different directions also.
Different directions, but they expect it to be an isotropic excess. But so in all directions, they see an excess and at different frequencies. And you can fit a power law through the excess as well.
Okay.
So that's the confusion.
Thank you.
Yeah.
Thanks for the nice talk. So I think the signals will be really weak, right?
Yes.
So
Actually, it would be nice from now on if you could just mention who you are and then ask.
okay. Okay. So my name is Paromita. I have come from Ohio State University. Yeah. So the signal will be really weak, right? So what would be the threshold for the signal to noise ratio or the power that you expect to trigger on?
Yeah.
And do you have any implementation of any like beamforming kind of triggering thing? Yeah. Thank you.
Thanks. So the signal is very weak. The good thing about the signal is that it is isotropic because it's in the spectrum of the CMB. It's not coming from a certain direction. We don't have to beamform. Maybe we have to beamform just from a foreground separation point of view. But for the signal itself, we don't need it. So we prefer having a very, very wide beam so that our signal to noise ratio improves. And I think you asked about the threshold, right? Okay, so we have done some simulations just from somewhat ideal settings. And we think that for a signal detection, not a measurement, for a signal detection, we need an array of these radio telescopes, the kind I showed you. We will need 128 of them going on the sky for one antenna year altogether. That will give us about a 3 sigma detection. So that's the expectation we have now. So it is quite futuristic, but yeah, we're kind of chipping away at it one layer at a time.
Thank you.
Yes. Can you take the mic from there?
Hi, ma'am. I'm Tanisha Kiran. I'm an undergrad at Rajarajeshwari Institutions. So it was an amazing talk, by the way. So I have actually a very stupid question, but then I'll just short it. So what is the algorithm that is used to separate the cosmological signals from the foregrounds?
Yeah.
So that,
Yeah, I didn't spend much time on it just to get to this part. So it's a very simple algorithm. We have devised a class of polynomials that we call maximally smooth polynomials. At the end of the day, they're just like a monotonically increasing or decreasing function, which means you are not able, this function that we use for foreground separation cannot fit to any data that has inflections in it. So if something goes up and down, the algorithm will not fit to that data. Okay. And we use this because the signal has this up and down type of signature, like a sine wave, but the foreground does not. Foreground only goes down smoothly like this. So this algorithm will fit only to the part that goes down smoothly, and whatever is left behind, this ripple-like structure should be from the cosmological signal. But if you have your own instrument introduces this kind of up and down signature, the algorithm will fail. Okay, so which is why we try to put in a lot of effort in designing an instrument that does not give these fake signatures.
Thank you.
You had a question? You'll have to borrow the mic from there.
Yeah, nice talk, Mayuri. I just had a curious question about this waveband which is chosen for the design of this experiment. And are there any previous attempts made in this direction or in this energy band, or what would be the difference in the instrumentation you are designing? So it's just a curious. I'm not from this.
So the reason we chose this band, like I said, is to maximize signal to ratio. We are not the only experiment operating in this frequency range. There are other radio telescopes like VLA, many of them. But the reason why we are slightly different is that we are focused on what we call absolute temperature measurement. Which means we are not calibrating off of radio sources. We are actually putting a number to the temperature we measure as part of our calibration strategy. That is why we are unique. So in this frequency range, there are, like, as to my knowledge, 2 other experiments that are doing exactly what we're trying to do. One is RK2, that was a balloon-borne experiment decades ago, 2011-ish, I think. And that did at spot frequencies, so 3.3 gigahertz, 8 gigahertz, like that. And there's another experiment called TRIS. That is probably the most comparable. Again, that observed for a while, and they produced their data, and they placed some limits on the CMB spectral distortions. So as of what I know right now, for this science goal, we are probably the only dedicated experiment in this band.
Okay, thanks.
We can compromise on tea if you want, and we can ask more questions.
Or we can talk over tea as
Or we can talk about. Okay, I have to say, what a great experiment, nano Kelvin on top of.
Thank you. I get there.
And I just wanted to understand this. So the cosmology or the astrophysics that you mentioned was helium abundance.
Yes.
But what else can we get from doing this experiment?
Mostly, okay. So if you at this point, if you go for the standard prediction, this I'm showing here, it is mostly a verification of lambda CDM. So if you go beyond detection to this measurement regime that I said, of course, you get helium abundance. It's also a very, very complicated way to verify some cosmological parameters like Hubble constant, CMB temperature, and theory papers that have been motivated by non-standard physics as well as non-standard processes of energy injection, like some dark matter annihilation and so on, in which case the signature you see will be very different from the lambda CDM.
Okay, thank you, Mayuri. And